Hey Sudipto, are you able to hear me? All right, great. Sorry for the trouble. Did you end up in the second meeting, the link that I just sent, or did you just join to the correct one? So for some reason, the usual Zoom meeting wasn't working for us today. I guess the problem was just temporary, and after a few minutes, it started working. So I thought rather just let's be on the same meeting. Let's just wait over here for a few seconds for others to get to the same meeting as well. And we'll just get started in 1 or 2 minutes. Sorry for the trouble again. But were you confused on which meeting to join? Did you look at the WhatsApp message that I just sent? And I guess today, yeah, I just deleted it because as soon as I sent that message, no, the previous meeting started working again. I guess there was some issues from their side. But anyways, it seems like it is one of those days when everything that can go wrong is going wrong. But hopefully, we don't have much trouble going ahead in the class. The internet looks good today. Hopefully, I'm able to get back to the office and everything is good in our building as well. So hopefully, it goes smooth ahead in the class. So give me just 1 2 minutes over here. Let me just settle down and make sure that everything is set up properly, and then we'll get started in next 2 minutes. All right, so let's get started for today's class. In our today's class, we'll be going over uh, support vector machines. And Sudipto, just let me know if you are able to see the screen properly and the voice is correct so that we can move on with the class with the support vector machine. Okay, great. All right, so let me know whatever we till now what have we studied about classifiers in general. I just want to revise a few things before we move ahead. So can you recall a few things from our previous classes, some concepts that we have studied? yeah, we started off with gradient descent, right? So we know that given a optimization problem, if we know this function, if we know this function, we call it no, j theta sometimes, no, j omega, whatever you want to call it. If we know this function, we can take a derivative of this function and then adjust the parameters of our model delta m and delta b such that we reach to a point which is lowest on this curve, right? So if we know this loss function, we can reach to the bottom using the derivatives, right? So is that something that we have already studied in our previous high school classes? If we know this function, we know how to get to the bottom over here, right? What we could do is take a tangent over here, take the slope, and should we move in the same direction of the slope or in the opposite direction? We always move in the opposite direction, right? So we also always want to have delta m, want to adjust m such that it is in the opposite direction of delta m. And again, should we go, now what was the factor that we multiplied it with? We multiplied it with a small factor over here, the learning rate, right? So that if we are too high on this slope, we don't move by an infinite amount. And if we multiply this with a small amount, we know that we'll take small steps towards the bottom of this pit over here. Okay, so this is what we have seen in our gradient descent class. And today we'll be doing something similar. The only thing is we'll try to see how we can change this function on which we're taking the derivative such that we get a better model of a better classifier than what we did with logistic regression. Okay. Okay. So for some reason, I can't hide this thing. I don't want lock. I need to hide this thing so that I see my pointer over here. But for some reason, this thing is not going away for me today. That's weird. Anyways, as I said, this is one of those days for me when everything which can go wrong is going wrong on this computer as well. But let's see. Okay, so that was the quick recap. And then again, we then also saw linear regression for classification on in terms of what can we do with a linear regression. But what we saw was there were some problems with the linear regression for classification problems, right? Because what we said is if we end up in a point where we have too many x's over here, a linear regression model will tend to go towards this side, which is not what we want, because then we'll end up misclassifying these points, right? So these are misclassified. So that is not what we want. And that's why we said, instead of doing this, we can pass it through a sigmoid so that we, rather than having a linear model, we try to model the world using a sigmoid, something like this, right? So that in that way, adding more points over here doesn't affect anything. Then we saw the logistic regression and we implemented that in Python as well. And today we'll be focusing on support vector machines. This is something that we have already seen. The machine learning problems are of two types: the linear regression problems and the classification problems, right? So in the classification problems, we are given a set of movies and we are trying to find whether the user will like them or dislike them. Okay, so something that we already seen, just wanted to go over these slides again so that it's fresh in your head. So we know that we want to draw this line, okay, and we have done this using logistic regression, but there are multiple solutions to this, right? There isn't just one line that we can draw which is separating these two classes. And our interest today is to find a better line such that it it gives us better results during the test phase as well. So by looking at these three lines over here, can you tell me which model is a better model, just intuitively? Okay, so you think L3, and that is a correct answer. And what was the intuition behind that? So we know that L1 can't be true because L1 is misclassifying some blue points. L2 over here, and the choice is between L2 and L3. Both of these are classifying all the blue points correctly and the red points correctly. But why do you say L3? What is the intuition behind that? Hey Sudipto, are you able to? Yeah, so the question, I was waiting for you to answer over there, but the question is, do you, are you still able to hear me now, or is it not audible? So the question is, what is the intuition behind L3? Like, why is L3 a better model? Well, the L2 is separating these two features as well, and not just features over here, these data points. Okay, so you mean that L3 is right in between over here, right? So L2 over here is also separating these two classes, but it is closer to these blue points than this red points, right? And in machine learning, we generally don't want to come up with a problem which works only for the test phase. So L2 is working for the test phases, right? But intuitively, what we want is a line which is which is best separating these two classes such that it is not committing to either each of the class, right? So what we could think over here, that L2 is more biased towards these blue points. Will you agree with me on that? That L2 is more biased to the blue points, and L3 is not biased, or what we could say is a more generalized solution to our problem rather than L3. And this is what we are trying to do with SVM as well. So what we did with logistic regression, there is no guarantee that we'll end up with a best margin classifier, or a classifier which is best separating these two classes. But with SVM, we'll try to do it, we'll try to formulate our problem such that we end up with a line which is best separating these two classes. Okay, and that's the basic intuition or the need behind SVM, saying that. And I'll go over what do we mean by support vector machine, why is it called support vector machine, and why is that a fancy name. But in general, at a high level, I want you to understand the need for SVM. The need for SVM is we want to create a classifier which has a maximum margin between these two classes. Okay, and that's why it's also called a maximum margin classifier. Okay, so that is the motivation behind SVM, and to give you, some brief history about SVM. It is not something which is of recent days, or like it was formulated back in 1960s. And then there was this person, the Russian mathematician, who formulated it. Then he went to the US, and then he started working at the AT&T, the Bell Labs. And once he was working over there, he saw that there were some other scientists who were working on a digit recognition problem. So they were working on a problem to recognize handwritten digits. So whether it is 1, 2, 3, 4, and so on. And all the methods that existed at that time, they were not giving any good accuracies, or they were not giving any good results. And what he said was, you know what, back in 1960s, I have formulated a method which could be applied over here. And that's where he applied SVM to solve this digit classification problem. And that is what we are going to do tomorrow in our class as well. We'll take the same problem that he solved using SVM, and we'll try to do that in our class tomorrow. What usually I have done before is try to do both of those things, the mathematical derivations and the implementation, in one class itself, but that has confused some students in the past. So today what I'm going to try to do is we'll just do the mathematical model and the problem statement formulation for SVM today. So we'll do the math today and give you some idea on how the problem is formulated. And tomorrow we'll implement the digit recognizer system in Python. Okay, does that work for you? So that also means that we might not need entire 2 hours today. We might just need half, or no, one and a half lecture today. But the whole idea is to let you sink in those concepts rather than trying to rush the 2 of the classes together. That's what I have experienced, that it's better to just split that into 2 classes rather than trying to do both the mathematical formulation and implementation in the same class. Okay. Are you with me on this one? Do we understand how, what's the motivation behind SVM is to find out a classifier which is best separating these 2 classes, and that's why it's also called a maximum margin classifier. Okay. All right. So let's see, how can we find such a line or such a plane which will best separate both these 2 classes. So it's not like linear regression. First of all, a support vector machine can be used for both a classification as well as regression problems. Okay, so if you go and look in scikit-learn, you will have both a support vector machine classifier, which is SVC, and also a support vector machine regression method which is available. Okay. But generally you'll see that support vector machines are good for classification tasks and not really used for regression problems. So we are trying to find a line which is best separating both these 2 classes, but doesn't mean that we are trying to make predictions on this line. So it's not a regression problem that we are solving. Does that make sense? We're not trying to find points on this line. We're just trying to find a line which will best separate both these 2 classes. Okay. All right. So magically somehow those points disappeared, and that's what I intended. But as I said, I'm trying to get to the eraser, which is somewhere over here, but I can't get rid of this taskbar in the full screen menu as well. Okay. Anyways, so let's revise some maths over here. Rather than trying to derive a few things, I'm gonna try to give you some intuition behind how these equations are functioning. Okay, so over here, how can we mathematically formulate which side of the line we are? Okay, so over here we want to say that if this blue point in our algorithm, we want to say if this blue point is on the left of the line, then classify it as the user will dislike it, or if it is on the right hand side, then we will we want to say that the user will like it. So how do you put it mathematically or in the form of equation, or how do you even put it in your algorithm. Any thoughts on this? How can we find which side of the line this point is? Any thoughts on that? Now, just by looking at it, you can say that, this blue point is on the left, but how do we put it in our algorithm? Okay, so you're going to plot that line. So this line you already have, okay? So you have this equation of this line, y is mx plus b. You have this. And you want this line, you want this point over here, you want it, whether it is on one side of the line or is it on the other side. So how do you differentiate that? Okay, so it's not that straightforward. Obviously, as you are thinking about it. So you say that we need to draw horizontal and vertical lines from that point. Okay, so if you draw horizontal lines and then check what point it cuts on that line. Okay, so let's say if you are over here, whether if you draw a line from over here or over here, how is this going to be different? And if you think about it, there is nothing like drawing a line as such in your algorithm. All you are saying to me is you are going to check the y value of this point and the x value of that point. Is that correct? So if this is 3,3, you're seeing that where does it cut, or what is the projection of this on this line, right? Okay, so that is what intuitively you are getting close over there. So let me just show you how you could do that as well, and that is correct. We need to project the point to the line, and that will give us a sense of now where this point is located. Okay, so let me show you how. What if I said, now let's see if you agree with me on this one. If we do this, if we project the point onto that line, so projecting that point onto the line is nothing but saying taking a dot product of the parameters of that line and multiplying that with the point itself. Okay, can you try to take the dot product of this line? So let's say this line is passing through origin over here. So y, the mx plus b, and what is w over here? This is the same parameter vector, the theta that we spoke about yesterday, okay, last time. So now I'm just representing it with w, saying that these are the parameters or the weights of that point plane. Okay, so over here, let's say the slope of this line, let's say this is -1, and this is passing through origin. Okay, so the parameters of this line is -1 and 0. And let's say you take a dot product with this point, -5, 0. Can you go ahead and do this matrix multiplication? We are taking a dot product of the parameters of that line and the point itself. So let's say this point, green point over here. What will be the answer to this? Okay, this will be +5. All right, and what can you do it same for the red point over here as well? So you got a positive value over here. Can you do it for red point as well? So again, you have -1, 0, and you have 5, 5. And it will be -5, right? Okay. So now can you think, now do you get a sense that now if I tell you, you can verify it, that any point which is on this side of the line, okay, any point you can select, and if it is on this side of the line, and if you take the dot product, or if you take the projection, you'll get a positive value. And any point on the other side of line, so go ahead and select any random point and try to take the dot product with it and see if you are getting a positive value for that point. So let's say this is maybe again this is 5, and so go ahead and verify it. Okay, so I just gave you 2 examples over here, and go ahead and do it for any random point. And what I'm telling you, a statement that I'm making over here, is anything which is on the left of the side, left hand or one side of a line, you'll get positive values, and anything on the other side, you'll get negative values. So you are saying for 0, -2. So if it is 0, that means that the point lies on that line. So if this slope is -1, okay, so if you have 0, -2, okay, so this is the point that we are talking about. Okay, so let's say 0, -2, so -1, 0, and you have 0, -2. So this is -1 times 0, which is 0, -1 times -2 as well, right? So +2, plus 0 times 0 and 0 times -2. So you got +2 over here, not 0. So you multiply this with this, plus this with this as well. Is that correct? Yeah. So everything on the left hand side, you will see that it is the projection will be positive, and everything on the other side you'll get a projection that's negative. Okay, so keep this in mind on how do we go about finding out on which side of the line we are. Is all you have to do is just take the dot product of the point with the parameters of that line or a plane that we are working with. So 5, 5. Let's say if we have 5, 5, -1, 0, and you have 5, 5. So we'll have -5 plus 5, or -5 minus 5, right? So this will be -10. Yeah, so that will be -10. And I guess I made a wrong statement then, that if the point is on the line itself, then you will get 0. I don't think so. The projection won't be 0, I guess. It should be. Or what we are seeing over here is that there is some magnitude associated with it as well. I'm not sure. So I'll see if what the value should be if the projection is on the line itself. But I thought it was supposed to be 0, because 5, 5 is on this line, right? And we are getting the answer as -10 over there, right? So I'll check why I thought this has to be 0 over here, because only then we'll be able to see whether it's on the one side of the line or the other side. Okay, so you verified as well on what that answer should be for any point which is on that line. So Sudeep, though, actually my mistake over here, 5 comma 5 is not on this line. 5 comma 5 is over here, and as I said, over here as well. So this is what you were saying, that this is -5 and -5. Yeah, that is correct. So this is -5 -5. This should be -10. So this should be -10, but this point is not on this line, so we have this as a negative value. So I thought 5 comma 5 was on this line, and that's why I was wondering why we are getting a negative value. But anything which is on this line, so let's say -5 comma -5 comma -5, that should be on this line over here. So if you have -5 comma -5, you will get you should get a 0 value over there. All right. So our objective is to find a plane which best separates these two classes over here, right? And we know that any linear function over here, so this linear model can be represented using the parameters of that line plus the offset, because right now b is 0, so we don't care. But if we had some offset on the y-axis, that will be the y coordinate that I'm adding over here, right? So we know this, our objective is to find a plane which best separate these two classes, and this is the general linear model of the line that we have already seen, which is the parameter vectors times x plus the b. It's just saying it's mx plus b. Okay. So over here, I'm drawing two more lines now. The first line over here, I'm saying that let's think I want to draw a line, this blue line, such that it is right in between these two classes. Okay, so let's see if we draw two more lines over here such that for the equation for this line will be wtx plus b equals to -1 and wtx plus b equals to +1. All I'm saying is now this +1 -1, where did this came from? I'm just saying it is at a constant distance. Okay, it could be -5 +5, doesn't matter. All I'm saying is, let's say if we draw these two more lines which is at a constant distance from these two lines, again these are the parameters of the plane, and if we draw these two lines, can we now find the distance between these 2 points, these two lines? Our objective is to maximize this distance, and I'm saying you that I've drawn these two lines now. The first one is wtx plus b equals to -1, and as I said, everything on the right hand side of this line we are getting negative values, and everything on the left hand side, on this side, I'm getting positive values, right? We have already seen that. And the b is because we have an offset over here, right? So that's the b. But now can we find the distance? Can you go ahead and find the distance? What could be the distance between these two lines? Our objective is to maximize the distance, and that's why it makes sense if we know the formula for that distance, then it will help us going ahead. So Sudipta, yes, that's the statement that I made. So it is necessary that we know get, because we want to get a distance which is no the minimum distance, or the we want this angle to be 90 degrees, right? So it's like almost like, think of that this blue line is stretching its arm, and it is such that now we want to go we want to extend our arms unless it reaches the red point over here, right? We want to stretch our arms. So it is similar to know what we were doing, know what we do in our school. In our school days, a teacher would say, no, no, stand in a one hand distance, right? So we'll extend our arms until we reach to the front person. So think of this as, the blue line trying to extend its arm, and we want to find the distance between these two lines over here. So in our case, these two lines will be parallel, and the reason why they will be parallel is because we are saying that they are at a constant distance +1 and -1, right? So this is at a constant distance from these two. There is a constant offset over here, right? So this is a constant offset on this side over here. So if you extend this, that's a constant offset on the positive and negative side. So our objective now is to find this distance over here. So I think here's what your question was, is, if you have this, right, and if we have points over here, right, and let's say I have these two lines now, right? If I have these two lines now, do I want to find this distance? And my answer to you is we don't want to have these points over here. We don't want to draw such lines, because in that case, this line that we will find won't be the ideal line which is best separating these two classes. We want this line to go from right in between over here. And if we want the line to go in right in between from over here, we want to have these two lines which are also parallel. Does that make sense? If we try to draw lines which are not parallel on either side, then we won't get a line which is best separating these two classes. So given that, is there a way where we can find the distance between these two lines over here? So here's what we could do. We know the equation of the two lines over here. I took the equation of the first line, WTX1 plus B. So let's say X is X1 over here. So this is the first line, WTX1 plus B equals to 1. And I subtracted that from WTX2B plus 1. This is equals to -1, right? This guy. If we subtract these two equations, we'll get WTX1 minus X2 equals to 2 over here, right? And if I divide this with the magnitude of W over here, right? So this is a vector, W transpose, or a W is a vector. So if I divide that by the magnitude of vector, right? Because I want to get rid of this term WT. So there are two components to it. We have the magnitude as well as the direction. right? So I'm dividing that with the magnitude. So the only thing that is left now is this direction now. Okay. So we can't divide both sides. We are interested in this x1 minus x2. We are interested in finding what this x1 minus x2 is, right, for these 2 points. But we have this w term over here. So if I divide both sides by the magnitude of w, I can't divide with the vector itself. But if I divide by the magnitude of w, then I can cancel these two magnitudes. And the only thing left now is the direction, in which the direction for, and it happens to be this direction, right? So this direction, if you look at it, it will be this particular direction along which we are measuring the distance from. And the answer to that will be 2 by mod of w. Look at these steps over here and let me know if that is clear. So the final answer is the distance between these two lines over here is 2 by mod w. Okay. And the way we got it is we subtracted these two equations. We subtracted equation 1 from 2. We got wt x1 minus x2 is 2. So yeah, it will be a constant factor, whatever we take. If this is plus 1, minus 1, right? So if we take minus 5 plus 5, that will be 10 then, right? So it's just a constant divided by magnitude of that vector. Okay. But so this is the distance that we want to maximize. But are there any constraints to how much can we maximize? Yeah, the red point should not cross any data. So this is the optimization problem that we have at hand, that we want to maximize 2 by w, but such that this is our constraint, such that wt xi plus b is always greater than equal to 1, right? So these points are always greater than equal to 1 for yi equals to 1. And for yi equals to minus 1, yi is the output that we want to predict, right? So whether this is a red point or a green point. So over here I'm saying is for positive values, for yi is equals to 1, I want all wt xi plus b, the equation of this line, should be always greater than equal to 1, right? So this green point should lie either on this green line or on the on this side of the green line. So this is always greater than equal to 1, because we saw from, and this is why I'd shown you before as well, that if you take the dot product with the parameters, dot products of the parameters with the point itself, we'll always get a point on this side of the line, right? And that's what we are saying over here, is that we want this line such that everything is greater than equal to 1. So either it is on this line or it is on this side. And similarly for yi equals to minus 1, we want wt xi plus b is always greater than equal to minus 1, right? So it's everything is on this line or it's on the right hand side over here. So this is our optimization parameter, and this is the constraints under which we need to optimize. Does that make sense? And look through it closely. It's not that straightforward as well, but that's the reason we are just going to go very slow today, and we're just going to cover very limited material as well. I don't want you to confuse this derivation with the implementations that we are going to do tomorrow. Okay, so and again, once you look at it tomorrow as well, or no, once you watch it, once you watch the recordings, it might be more clear on why is this the constraint over here. You can put that in the equation, and you can find all these points will satisfy this equation over here. Okay, just take some example, and you'll see that everything on this side, all these green points will have wt xi plus b greater than equal to 1. Okay, just put it in an example, and you will see that this will hold true, because everything over here will be greater than equal to 1. So our objective is to maximize the margin but still make the correct predictions, and this is what we are saying over here, is maximize this margin but still make correct predictions. You don't want this green points to be gone on the other side. So we want maximum 2 by 2, 2 by mod w, such that the equality that I just said. Now I'm simplifying this equality to this one. And can you think why I can do that? I'm saying this whole thing can be also written as simply this. And can you see why I can do that? Or can you tell me why I have done that, or why? Not necessarily why have we done that, I'm just simplifying it for our purpose. But how we could do this? So let me give you a hint over here. What happens if you multiply both these no, equalities with yi? So if you multiply yi over here and yi over here, so this is the form that I'm saying, right? So yi multiplied by wtxi plus b. So what happens then? Yep. So if you have yi equals to 1, right? So this will be 1 times, so that remains the same. But if you put yi equals to minus 1, now this equality changes, because you multiply both sides by minus 1, then this equality will switch over, right? So both equations will result in the same answer. Okay. So our problem boils down to this, is maximize 2 by w such that yi times wtx plus b is always greater than equal to 1. Okay, so this is our constraint and this is our problem. So the final equation that SVM tries to solve over here is this one. Is now, instead of writing maximizing 2 by w, can I switch that and say maximizing 2 by w is equal to minimizing w by 2? Is that correct? And can you think on why would I choose to minimize something rather than optimizing it or maximizing it? Why are we interested in minimizing w by 2 instead of maximizing it? Because have we already solved? So not necessarily because of that, but do we already know how to minimize a quantity? Given an equation, can we always come to the bottom of this pit over here? Yeah, we can always take a derivative. So if we take a derivative of this function, we'll know how to adjust our parameters, right? So similarly, like we were doing in the gradient descent, when we can apply j theta, and if we have the equation for j theta, then we can go to the bottom of this curve. Similarly, what if we have this SVM problem? If we know the equation of the loss function, we can always reach to the bottom of this loss function by taking a derivative of this. Okay, but I'm adding a few new terms over here. As we spoke last time, is that you don't always want to have a model which works perfectly in your training point, because there could be a chances that you are overfitting it, right? And that's the reason we are adding these new terms over here, which will loosen our model a little, right? So we are allowing for some errors to occur. We don't want to always find a line which will work 100% in our training case, and it might fail during the test phases. So what we will do is add some extra terms, which is also, which will loosen our model. This is also called as soft SVM. Okay, so we are allowing for some errors, so we are being a little soft over here. So for the soft SVM, what we could do is add new terms. The first term that we can add is called as C, and the C is also called as the regularization parameter, which will determine how many errors do we want to allow. Okay, so this is determining how many errors to allow. And then we also have some slack variables. These are called as slack variables, or you can pronounce it as xi, and these are the magnitudes of the error that we are allowing. So if this is 3 and this is 2 over here, and let's say I'm allowing for 2 errors, so this entire thing will be multiplied by, so 2 errors times this 3 plus 2, right, will be 5. So because I'm adding all the xi's, right? So do you understand now on how can we loosen our SVM model as well to get soft max SVM? So what we are saying is we'll allow for some misclassifications. In this case, we are allowing by a factor of C times summation of the slack variables, and these slack variables are nothing but the quantities that you are allowing for. So let's say if this is 3, this is 2, so you'll add 3 plus 2, 5. So how to determine what C should use, how to determine how much error to allow. Now these are called as the hyperparameters of your model. Okay, now these hyperparameters are nothing but constants that you have introduced, which you need to find answers to. Okay, and the way we go about finding these hyperparameters are usually there are some systematic approaches as well, but it's also trial and error. Okay, so a lot of times this is you try to change some numbers in your model. It was just like when we had learning rate in our gradient descent algorithm. For one particular problem, some learning rate would apply, and for some other problem, other parameters or other learning rate would work much better. Does that make sense to you? That these are hyperparameters that we need to actually optimize, and we don't know how to find them mathematically. Okay, but all we are saying is this is the final problem that we solve using SVM. I'm not going to go into taking the derivative of this equation over here, because that would take at least 2 days for us to reach to that point in terms of if we go about how to find the derivative of this equation over here and how do we go about finding it. But the takeaway that I wanted to leave you with in this theory section over here is that this is the final optimization objective that SVM tries to solve. It's a large margin classifier because we have formulated our problem such that we are assured that we'll always get a line as we said, this was +1, -1. We'll always get a line which is right in between over here. We don't want a line which is somewhere over here. Okay. Any questions until this point? Okay. So what happens if data is not linearly separable? Till now, we have seen that all our data points were linearly separable. But what happens if our data is not linearly separable? Now, is there a line can you draw on this plane over here such that it will perfectly separate two classes? We have two classes over here. There are x's and the zeros. Is there a line that you can think of that will best separate these two classes? But what now? I just added another feature over here. So I had just x before. Now let's say if I also consider x square now. Now, do you agree that we'll transform our data set to something like this? If I consider now from one dimension, I'm looking in two dimensions now. And I'm also considering x square. Now is it possible to linearly separate these two classes now? So Sudipto, again, my question over here is, we had these set of points and there are two classes that are available with us, the zeros and the x's. In one dimension, you said that it was not possible for us to separate these 2 points. We can't draw a line such that it will best separate these two classes. Whatever line we draw, we'll end up misclassifying something, right? Whether we draw a line over here, or somewhere. But is there a way we can still do it using the techniques that we already know? And my hint over here to you is, if we also consider x square, we also add another dimension to our data set. You know x, you can always calculate x square. And now in this two-dimensional plane, x and x square, do you think we can linearly separate these two classes now? Hey Sudipto, let me know if you are able to hear me properly or if you're thinking what's going on. Hey Sudipto, are you able to hear me properly? Did you got dropped off? Okay, great. So let me now go back to what I was mentioning over here. Is in one dimension, I said that we can't separate these two classes using a line. There wasn't a way that we could have drawn a line such that it correctly classifies these two classes over here. We have the zeros and the x's. And what I said is, what if we add another dimension over here? We consider x square as well. Now, do you think? So yeah, that is one thing that you are that you are intuitively doing is, if we draw a circle over here, then we can separate these two classes. But I'm trying to use whatever we have formulated until now. We know how to draw a line. We know the mathematical models for those things. But instead of drawing a circle over here, which is, you're doing the same thing. You're considering x square over here, right? So the equation of this circle will be something like x square plus y square is equals to something, right? So x square plus I square is r square or something like that. But over here I'm saying that if we consider, is there a line that we could draw, not a circle? You're not considering adding more dimensions over there, but is there a way we could linearly separate? That's what I'm saying. Is it linearly separable? So what you said is, yes, we can't separate them linearly. We can separate them using a radial function over there, right? Uh, and intuitively, we are doing the same thing. What I'm saying is, what if I want to linearly separate them? What I could do is have x and also x square over here. And if I consider now another dimension, which is x square, that is what you're doing over here intuitively as well. And if you have x square plus y square, then you can draw a circle. That's what I'm doing over here. I'm transforming the x's into a higher dimension. I'm saying I have x and now I have x square. Now can we draw a line in this plane to linearly separate these two classes? Yeah, we can obviously draw a line somewhere over here. Now this will separate these two classes perfectly, right? So that a takeaway from this one would be that this ties back to what I was mentioning yesterday. Is given enough dimensions, or if you have if you keep adding more dimensions, there will always exist a function that you can come up with that will approximate all the points that you are looking for. Okay, so given enough dimensions, now you can always find a perfect classifier. But going ahead, we'll also see why this is not a great idea of adding too many dimensions to your model, right? So when we go into dimensional reductions and those things, we'll see that why this is not a great idea on keeping on adding dimensions to your data set. And this is also called as curse of dimensionality, just to mention it over here. So it's called curse of dimensionality. Good thing is we could achieve tasks that were not possible for us to just draw using a linear kernel. But if we transform it to a space, if we increase our dimensions, if we increase our outlook a little, then we can always draw a line which will best separate these two classes. And similarly, there is another example over here. Over here, my points are in, over here I was going from 1 dimension to 2 dimension. Over here I'm going from 2 dimensions to 3 dimensions, right? So all these points are scattered like this. Now I can't draw a line over here. As you said, we could have drawn a circle, but the models that we have seen until now, logistic regression, support vector machines, right? So if we are drawing support vector machines, the equation that we derived, we are deriving it for this particular line. We are saying theta transpose x, or WTX plus b equals to 1. What if you want to apply the same model to linearly non-separable data? Well, all you have to do is just pass that through a kernel. And in this case, if you pass it through a radial basis function, that is also called as RBF, and we'll see if we can use RBF tomorrow in the class. So if you pass your data through a radial basis function, it will now get onto a Gaussian surface. So now we have a 3D surface like this, right? So now can we linearly separate these two classes now? Now can we apply SVM over here? Can we apply our logistic regression model? Yes, now we can do that. Does that make sense? Over here, I'm going from 1 dimension to 2 dimensions, and over here, I'm going from 2 dimensions to 3 dimensions to make it linearly separable. And the reason why we are doing it is everything that we have derived until now, it was working from a linear model that we started off with. Okay, so here are the last two slides that I have for you today. We'll just try to summarize whatever we have learned in these two quizzes. So for a given SVM classifier, you see that your model is misclassifying majority of data points. How would you adjust the regularization parameter? Will you increase C, decrease C, or set C to 0? Now, again, let's look at the equation over here. So right now, during our training phase, we are making a lot of errors. During our training phase, we are getting a lot of errors. So should we increase C or should we decrease C now? So Sudipto, why do you think we need to increase C? If you increase C, what is going to happen to the eventual result? So the C or the regularization parameter is defining how many errors to allow. We are already getting a lot of errors. So does it make sense to add more C to our model? Or do we need to decrease it? During the training phase, this is what I'm saying, is during the training phase itself, we are getting a lot of errors. So think of it like, most of the points we are misclassifying it. So we need to decrease C, right? If we decrease C, if we decrease C, then we are allowing for less error, right? So whenever we take delta of this thing, we want to make sure that no, we are allowing for less errors. That's why we'll decrease C over here. Okay. And let's do one more. This is the second one is a simpler one. So what type of kernel might be best suitable for this data set? A linear kernel, SVM with a linear kernel, or SVM with a non-linear kernel? Yeah, a non-linear kernel, right? So if we use a non-linear kernel, then we might be able to get a better classification over here rather than trying to fit a linear model. Okay. And again, it depends upon the problem statement and your domain knowledge as well. Okay, you might not always want to have this might also result in overfitting as well. So based on which you adjust your parameters. So within your RBF kernel as well, you will have some parameters. When I say RBF, I'm talking about the radial basis function. So we'll have the parameters of this Gaussian curve as well that you can adjust on how much you want this curvature to be. Okay. So that is something that we'll try to do tomorrow in our implementation phase, where we'll use SVM to make a digit recognition system, and we'll try to do it on the same data set, which was the first time when it was applied to digit recognition. Or in fact, actually, I don't want to do that. I just recall that I'll be using the same data. We'll create a data set by our own, and right from scratch, we'll do some image processing on it, and then we'll convert it to a CSV file, and then we'll apply the SVM classifier on it to recognize hand digits, to recognize handwritten digits. Okay. So that's it for today's class. I did not want to do both of those things in one class and confuse you a lot. So we'll be doing the implementation phase tomorrow. So that's fine, Sudipto. If you're not able to attend, we'll see. I'll check with the other folks as well. And if everyone else is attending, then you'll have to just look at the recorded video. Or if others are not attending as well, then we might just push the class ahead. Okay. All right. So thanks a lot for coming, and I'll see you next time. Yep. Goodbye.